Right, we're all familiar with acid-base titrations, and now we're going to have a look at redox titration. Now, in an acid-base titration, you normally put the alkali in the conical flask, and you put the acid in the burette, sometimes the other way around, and you find out the concentration of one of the two solutions that you don't know. Now, this is exactly the same sort of principle we're going to use in a redox titration, but instead of acid and alkali, you have an oxidizing agent in the burette and a reducing agent in the conical flask. Okay, now the oxidizing agent that you normally use, and the one that the board want you to know about, is that I've colored it in purple there because it's potassium manganate 7. Okay, so we need to know the Hoff equation for that. So manganate 7 ion is going to act as an oxidizing agent itself, is going to become reduced to the Mn2 plus ion. So balance for oxygens, we need 4 H2Os on the right. Balance for hydrogens, we need 8H plus on the left. Balance for electrons, balance for charge with electrons, well, we're going to need 5 electrons on this side. Now, you need to know that Hoff equation off by heart. It's really you need to know it. Now, the reducing agent. So the reducing agent, I'll put the red around that one for the oxidizing agent. The reducing agent can be one of two things. It can be several things, but the two examples the board want you to know, the AQA want you to know, is iron 2. So if you get Fe2 plus, it can be oxidized by the oxidizing agent to Fe3 plus. We need to balance that. We're going to just put an electron in there. Sorry, electron in the wrong place. Okay, so that is one Hoff equation. Okay, so if we put you need to know that one. Put a blue box around it for a reducing agent. And the other one that they want you to know about is the ethanedioic ion, okay, or the ethanedioic acid. So ethanedioic acid is like that. Okay, now when it's oxidized, it gets oxidized to carbon dioxide. And so we'll write the formula of that then. So just move that out of the way. Okay. Okay, so we've got C2H4, sorry, C2H2O4, and that gets oxidized to carbon dioxide. So 2CO2, right? All I need to do is balance for the oxygens are balanced. I just balance the hydrogen, so I need 2H plus there. And then balance for the charges, I need 2 electrons there. So you need to know that Hoff equation as well. Another variation on that is also the ethanedioate ion. It's exactly the same equation. I will write it down. So a minute. So you've got the two reducing agents in blue, and the only oxidizing agent that you ever put in the burette that you need to know about is potassium manganate. If you look at some old questions, you might see some old questions where they use the dichromate ion as the oxidizing agent, and that goes to Cr3, but that's officially off the specification now, so you don't need to know it. But if you do come across any old questions, that's the equation you're going to have to use. This ethanedioate one, you might see it as instead of ethanedioic acid, it could be ethanedioate ion. So that's going to be C2O4 2 minus goes to 2CO2. balance, no hydrogens to worry about, balance of the charges, 2 electrons. So it's essentially the same as that one up there. Right, now let's talk about how this works is, right, so if the oxidizing agent is potassium permanganate, it's important to realize you need some acid there. You need 8 moles of acid for every 1 mole of manganate. So you have to make sure you acidify the solution. So normally what you do is you prepare in your reducing agent, first of all, into the conical flask. So there's your iron 2, and then you add some sulfuric acid, usually excess sulfuric acid, and you don't need to measure that accurately. You just usually do it with a measuring cylinder, and put some in there and then start the titration. But you do need acid there. Right, now let's think about indicators for this reaction. Well, you'll see you actually don't need an indicator. The oxidizing agent here is purple. That's purple manganate ion. But when it gets reduced, it goes down to the Mn2 plus ion, and that's colorless. So as you let your manganate come out of solution, out of the burette here, right, it falls down into the reducing agent, and the purple color disappears as it turns into the Mn2 plus ion. And that will keep going until you get to the very end. When you've used up all the reducing agent, when that's used up, your manganate ion will persist. It won't get reduced. The manganate ion will persist in the solution. So that means the solution in the flask will go purple. And of course, if you make it go purple as such, you've gone past the end point. Really, you just want the first permanent pinkish tinge when you've just got a drop of manganate in there, which hasn't actually reacted. And manganate is a very intensely colored ion, so it's very easy to see even at very low concentrations. So it's quite easy to get a good end point. Okay, so that's why you don't need an indicator. It's self-indicating, if you like. Let's look at an example of a calculation, a nice easy one. So I've got one here. Right, it says here 25 centimeters cubed of a solution of iron sulfate were pipetted into a conical flask. So I draw a little picture there. So we've got a conical flask. We've got 25 centimeters cubed of our iron sulfate solution. And you add excess H2SO4, I won't worry about that. And then you titrate into there, there's 26.9 centimeters cubed of manganate. So here's our burette with a manganate in it, MnO4 minus. Concentration there, it says is 0.02, very dilute. It was a very dilute solution, but it still looked almost black because it's such an intensely colored ion. And we require 26.9 centimeters cubed of that. And we've got to find the concentration of the iron sulfate solution. Right, how are we going to do that? So we need to just very quickly write down the 2 Hoff equations. Well, the manganate is that's 8H plus 5E minus, goes to Mn2 plus and 4H2O. And the reducing agent, well, the iron is going to go to Fe3 plus an electron. So if we look at the number of electrons involved, we've got 5 there and 1 there. So what we need to do is we need to times this 1 by 5. So the molar ratios that we're talking about is 1 mole of manganate to 5 moles of Fe2 plus. Okay, so let's do the working out then. So, right, moles How many moles of manganate have we got first of all? We'll do concentration times the volume. So the concentration is 0.02 multiplied by the volume, 26.9 over 1,000, so that's 0.269 dm cubed, of course, and that is equal to 5.38 times 10 to the minus 4 moles of manganate. So now it's a 5-to-1 ratio, so therefore the moles of Fe2 plus is equal to 5.38 times 10 to the minus 4 times 5. And that is equal to 2.69 times 10 to the minus 3. Moles of Fe2 plus. So that means we've got how many moles of iron sulfate have we got? So moles of iron sulfate is going to be the same. And that was in a volume of, well, here, look, we had 25 centimeters cubed. Yeah. In 25 centimeters cubed. So concentration is equal to moles over volume. Is equal to 2.69 times 10 to the minus 3. 25 centimeters cubed is 0.025 dm cubed. Look at that. That gives us 0.1076 moles per decimeter cubed. I should give my answer to 3 sig figs because that's what most of the data is given to. So that's 0.108 moles per decimeter cubed is the answer. Okay, so there is a simple problem involving redox titrations. In the future videos, we'll do some more complicated ones, like finding out water crystallization, finding out percentage purity, and various other things. That's just a straightforward one.